is going to do a, anyone here, did you hear about this? Some of you did. Yeah, at 2:20, during your 2:20 class, all of your cell phones are going to ring, supposedly, if they've set it up correctly. Well, yeah, that just means that, yeah, it won't ring for 30 minutes. It'll ring.
Someone's phone might not ring at the same time as yours.
Yeah, true. I think, yeah, we'll see how that works. I'm not going to be in class. Yeah, that'll be fun.
Wait, what's this for?
FEMA and the FAA? No, not FAA. Federal, whatever the one that deals with cell phones. FCC. Yeah, they're testing like an emergency broadcasting system. Back in the olden days, back when I was a kid, I'd be watching my cartoons happy, and then all of a sudden I'd hear this beep. The TV would go like have this weird pattern on it, and then they'd say, "This is a test of the emergency broadcast system. This is only a test. If this were a real emergency, you would be instructed," whatever. So I'm assuming this is like the modern day equivalent of that. Everyone's going to get this. So this first time they've done this, no, they did it over the summer, didn't they? But it didn't go well. So they got to keep testing. I don't know. But anyway, I don't know why I thought of that just now. But yeah, let's get her done here. Okay, so plus 105 radical 3t plus c2 times j. Once again, the constants of integration, they aren't always going to be the initial conditions. However, in this one special case, let me just tell you the special case so that you know. When you're dealing with a polynomial and when the initial condition is a point when t, or the independent variable, is 0, that's the only time that you'll, well, maybe not the only time, but it's one of the only times that the initial condition is the constants of integration. So what is the initial position of this thing? R of 0 is going to be 0i plus 90j. How do I know that? Well, there's where the bullet is starting, or the shell, or whatever it is, the cannonball. It's starting right there, 90 meters above the origin. So without having to go through all the rigmarole, R of t is 105 ti plus negative 4.9 t squared plus 105 radical 3t plus 90j, which I know the physicists just skipped all of that and just got to this in one shot, right? Because there's that formula. You have negative 4.9 t squared plus the initial y velocity t plus the initial y position. That's the formula, isn't it? And then the x coordinate is always just the speed, or the x velocity. Yeah, let's not get too into that. Okay, so there it is. I'm done. No, I'm not. Let's go back here. So find the range of the projectile. So I need to know, sorry. That's what I need. I need to know what the coordinates of this point are. So that coordinates are going to be some value of x, 0 for y. So that's where the projectile hits the ground. So what I'll do is I'll set this equal to 0. Let's do that right now. T squared plus 105 radical 3t plus 90 equals 0. And then this gives me t equals, oh yeah, I'm not going to try to factor that. I'm going to use the quadratic formula. So negative b plus or minus the square root of b squared minus 4 times a times c. Is that right? I got all that. All over 2a. I'm just going to write this way. Okay, so we could do this. Wait, some of your calculators probably do this without having to do as much work, but I'm going to type it in. Now, before I type it in, there is a plus and a minus. You might wonder about those. Well, here's why there's a plus and a minus. is if you imagine this object starting out down here on the ground, this is the negative and this is the positive. We want the positive one. Oh, no. Okay, we want the one that will eventually be positive, and the one that will eventually be positive will actually be the negative branch because you're dividing by negative 9.8. Otherwise, when you divide by negative 9.8, you'll get a negative number. Okay, so let's see if I can do this. Oh, this is going to be too painful to type into my calculator. I'm just going to type it into the computer. Give me a sec. Okay. Just a sec. 105. Square root of 3. I know, so much here. 90. Okay, here we go. So, oh, how is that even possible? I made a mistake. I typed wrong. Let me try again. That's much better. Okay, so I got the answer that T is equal to 37.604. How many digits do they want? Oh, round the nearest whole number, I'm going to be okay. So if I use, usually if it says the nearest whole number, then you should definitely not use whole numbers for the intermediate steps. Like round to give it at least a digit or two. I'm going to go with 3. Okay, so does everyone see where this number's coming from? There's a second, here, I'll tell you what the other one is. So I happen to have it over on my screen here, is negative 0.488. There it is. One way you can think of negative 4.88 is, let's say that we fired this thing the other direction. Where is this? So instead of firing it up at a 60-degree angle, what if you fired it down at a 60-degree angle? Then it would hit the ground right there, and it would take 0.488 seconds to get there. It'd be like, done. Kind of dumb, though. Why would you do such a thing? Much more cool to shoot it upward. Okay, so those T's are okay. So anyway, I've got a value for T. That is the time of impact. I need to know the position. So the position is going to come from here. I just have to do X is equal to 105 times 37.604. This I can do on my calculator. Give me a sec here. Times 37.604. There it is. We have, 39.4, sorry, not point. Sorry, I was so focused on the decimal. 3948.42. That's really close to 0.5. And it makes me wonder if I had rounded early, rounded this, for example, that would be off by quite a bit. So I'm happy with rounding the way I did. So I'm going to go with 3948 as my answer for the distance. That's only part 1. Wow, are we going to do anything other than this today? We're going to find out, aren't we? So let's see, this is 3948. I know you don't have the luxury, or do you? If you were to do what I'm about to do, would you get docked for not having put anything in those? Like,
just waste a submission.
So I just wasted a submission? Is that what happens to you? For the answer, if you leave blanks, it doesn't take away from those? No. All right.
If you lose it, like total submission. No. Because it's submission
Oh, see, you learn something new every day. I don't know. I don't. Okay, so I wanted to just double check that number was right before I messed with the other two. Letter C, I'm going to do letter C next because that's talking about the speed at impact. And that is talking about this point that I have highlighted right here, that circled point. So how fast is it going? So what I need to know is I need to know the velocity. So where is velocity? Here it is. So I'll take this velocity and I will compute the velocity at 37.604, which is going to be this, this vector, 105 And then I have to do this, I guess, 37.604 times negative 9.8 plus, wait, is it plus? Yeah. 105 times the square root of 3. Let me make sure I've got all this typed in correctly. Does that look good? Hopefully. So I got negative, hold on a minute, where am I? Oh, there it is. So I'm getting negative 186.65. So there's my velocity vector. Does that look about right? We can pretend, it's fine. Okay, so we're going to use this. I've got it in my calculator, so I'm just going to square that and add to it 105. So I'm just doing squaring both of these, and then I'll do the square root of the result. And I'm getting as a velocity, or a speed, so the magnitude of this, the magnitude of v of 337, sorry, 0.604, I'm getting 214.16 meters per second. So let's see if that's right, 214. Since they only care about one digit, so 214. See if I'm right. I just wasted another submission. Yeah, for me, I have infinite submissions. Okay, yeah, I got it right. Phew. Okay, the final one. Where is this a maximum? So let's go find it. Look at that. There it is. There's the maximum. I mentioned this last time that the maximum will be the point where you have a horizontal slope. You have a horizontal slope when the velocity vector is horizontal. Notice that this velocity vector will be horizontal if this number is 0. So I need to figure out when is this equal to 0, and that's going to be when t negative 9.8t plus 105 radical 3 should equal 0. So that's when t is equal to 105 radical 3 divided by 9.8. As before, I'm going to write this to like 7 digits or something. So square root of 3 divided by 9.8. Let's see, I'm getting 18.558 seconds. Wow, that's a long time. Well, I guess that makes sense because it's taking like 37 seconds to hit the ground. That's right around the midpoint of that arc. It still feels like a long time. But anyway, so that's going to be the time at which it's the maximum. But to get the maximum height, I don't really care about the x value, but I do care about the y value. So the y value is going to be this right here, the thing that I've got underlined now twice and boxed. So I have to plug 18.558 into that nasty thing. It's going to be all right. So 18.558, I'm going to, see, give me a sec here. Fortunately, I've got it in my calculator, so I can just do this, multiply by 4.9, square it. Almost done. Add 90 to the end. All right, let's see if I got it. I got 1777.5. Wow, interesting. Yeah, I can't either. It's going to be fun. All right, so let's try this. So I'm going to go with 1778. If this isn't right, then I'll try 1777. Oh, I got it right. Phew. I wonder if 1777 would work. I know it's a different number, but let's just see what it says. I'm wondering, the reason is, I'm wondering if they allow for, oh, yeah. No. What they're doing is they are allowing a little bit of wiggle room for those of you who don't want that you rounded too much. So they're giving you a little, it wouldn't surprise me if 1776 worked. Let me check. There's probably at least a couple of, I think it's allowing a little bit of, nope, that doesn't like that. So 1779, I know, it's getting boring. We're right in the middle of the Revolutionary War now. Oh, it worked. Okay, so apparently there's several numbers that work. It's centered at 1777.5. Okay, so does that do it for us? We're done? We're done? We're happy? All right, well, let's get a much easier problem for the quiz. I probably should have had something hard for the quiz. Oh, yeah. Oh, I know what I'm doing with the quiz. Okay, so the quiz has 5 parts to it, but you only have to do the first 3. So you'll see that the other 2 we're going to be talking about as a group in just a bit. So do the first 3. We will talk about the last 2, and then I'll just give everyone 100% on the quiz if you're all so amazing. I don't have to give one amazing. So I'll put it up on the screen. There. Beautiful. So yeah, so those, oh, you can't see it. Still can't see it. So those 3. So A, B, and C. A, B, C. If you want to go on and do the others, that's fine, but I want to talk about those. They're special. Find this document. All right, let's see how we're doing. I know you're done, right? You probably did the whole thing, but let's go ahead and do this together. Make sure that you're all on the same page. We have V of t first. So this is going to be negative, oh, what am I doing? Doing it wrong is what I'm doing. Give me a sec. 1 times I plus 2t times j plus 3t squared times k. And so that means v of 1 is going to be I plus 2j plus 3k. So far, so good? We're awesome, aren't we? Okay, next. A of t is the derivative of v of t. I know you all did this correctly, so that's why I don't think I need to collect this. 6t. If you made a silly mistake, this is your time to learn from it. So take the derivative of velocity to get the acceleration. And then we do a of 1 is going to be just 2j plus 6k. Let me just write this as a vector. 2, 3, 0, 2, 6. In component notation, I know it's already a vector. All right, so we got those two vectors. Very nice. Now the speed. Now here's the thing about the speed is I know what you did. You took this thing, right? And you just did the magnitude of 1, 2, 3. And you got, what is that, radical 14? Okay, radical 14 is correct. I'm just going to do it a little different. It's almost the same. So here's what I'm going to do. I'm going to write the speed like this, the magnitude of the velocity. Yeah, so far so good, right? Same. Which is the square root. Here's where I differ. 1 squared plus 2t quantity squared plus 3t squared quantity squared. There's a reason why I'm doing it this way that will become evident momentarily. Anyway, that's essentially the same thing as what you did. It's just I'm doing it the long way. So now I get the magnitude of v1, which is, in fact, 1 squared plus 2 squared plus 3 squared, which is the square root of 14. Okay, good. You did it right. You did it right. But I wanted to do it this way so that I could explain these next two. So these two, I saw them on there, so I'm pulling, I'm trying to be as little work as possible, which means I've got a file on my computer chock full of quizzes. And so I'm looking for a quiz that matches what we did in class. And I see this, and I think, oh, close enough. But it has these two little nuggets that we didn't go over. And I thought this is time for a little bit more of a little learning thing. So those two things are super important, actually. So I know we didn't even talk about them last time, and I don't even know if we have homework on them, but they're really important. So let me just explain them really quickly, and then I'll show you how to get them. So this one is called the tangential component of acceleration. And this one is the normal component of acceleration. So that's what they're called, tangential component and normal component. Now, it'll become more evident once I draw a picture why we care about these two things. So let's draw a picture. So on your back of your paper, if you want, I'm just going to scroll up so that I get to the next page so I don't mess up here. But so somewhere, or you could not write it if you don't want to draw this, that's fine. You could do something like this. Here's my r of t. That's my curve. And then I might be interested in this point. So let's just pretend that that's the point that I'm interested in. So this will be the velocity is going the same direction. The acceleration, though, we don't know what direction it's going. It could be pointing the same direction as the velocity, although in this case it can't. I'll explain why in a minute. But it could roughly point the same direction. You could have an acceleration. If you're driving and you have your foot mashed to the floor on the accelerator, then even if you're going around a curve, your acceleration vector is going to be largely in the same direction as your velocity. because you're speeding up, and that's the majority of the change in your velocity is this speeding up business. Okay, so, but you could also be hitting the brakes, screeching to a halt, in which case your acceleration vector would be pointing in almost the opposite direction. The reason why it can't be pointing the same direction is because your acceleration, we hope, if you're driving on this road, you will be turning your steering wheel and you'll be adjusting, your velocity will be turning, and so you'll have some component, some portion of your acceleration that points towards the center of this curve in order to pull your direction, in order to steer you in the correct way. But anyway, let's get back to this. Let me draw an example of an acceleration vector. So your acceleration vector might look like this. It'll always be pointing some way towards the center of the curve if you're going to stay on this road. So it could be going backwards, but still towards, it will never point out here, is what I'm saying. Okay, so let's say that that's my acceleration. Now, I just mentioned two phenomena when you're driving. If you think of driving, that's a great example. If you're driving, there's two phenomena going on when you're driving around this curve. One of those phenomena is either you're pressing the brake or the accelerator. Brake or accelerator, that changes the speed of the car. So if you look at the speedometer, or maybe it's just numbers changing, that's what, so if you're accelerating this way, that's called the tangential component of acceleration. The other thing that's affecting your velocity is the curve itself, and that's going to be sort of bound up in what's called the normal component of acceleration. So as I'm driving, when I hit the gas or the brake, I'm going to be adjusting the tangential component of acceleration, and when I use the steering wheel, I'm either going to change that direction or it'll change the normal component. So here's how this looks. If I draw a diagram, I would have something like this. And then this, let's see, how about this? Because these are not vectors, they're scalars, they're numbers. So this thing is going to be A sub t, is how long is that distance there? How much of your acceleration is going into speeding you up or slowing you down? So that's A sub t. And then this portion here, that's A sub n. Now there's a whole bunch of different ways to compute these, and I'm going to show you the easiest, but I will mention the others. Yeah, the A sub n, that's how much of your acceleration is turning you. So I guess roughly what you could think of, if you're familiar with driving a high-performance vehicle, which my Prius is definitely not. But I used to have a Datsun 280ZX in college. That was a high-performance vehicle, and I used to drive it like an idiot. But the stupidity gene, it turned off when I turned about 25. Yeah, guys, your stupidity gene will turn itself off automatically when you turn about 25. I can show you the data to prove this, but we don't have time right now. If you take statistics with me, I always go over the stupidity gene. But anyway, getting back to this. Driving your high-performance vehicle, when you are pressing the gas really hard, you feel it in your back. You feel yourself being pressed into the seat of your car. It feels good, doesn't it? Anyway, you feel that. When you're turning your steering wheel, you feel yourself being jammed up against the door or maybe towards the center console. It's fun, isn't it? I know. When you're young, it is fun. It's scary when you're old. That's why I have a Prius now. But anyway, so the tangential component is how much you're accelerating yourself, and the normal component is how much you're steering yourself, how quickly you're changing your direction. So in order to figure these out, here's one way to do this. You can actually see this from this diagram. The tangential component, that is a vector projection. I am projecting the acceleration onto the velocity. Do you see that? It's a vector projection. So I could do this way, that A sub t, technically it's not a vector projection, it's a scalar projection because I don't care about the vector part. because I already know the velocity points that direction. So it would be this, the comp of A of t onto V of t. So you could work through the formula. That works. It is fine. You can do it that way. I don't like to do it that way, so I'll explain the way I do it. So if you want to work out that's going to be the dot product, just if you're like, what is that? Okay, it's A of t dotted with V of t all over the magnitude of V of t. That's the vector component. So that works. So if you like it that way, you do it that way. Oh, another way, by the way, is, so this is going to be A sub t. There's a whole bunch of ways of doing this. You can do the acceleration dotted with the unit tangent vector. I don't recommend that at all. That is not fun. But that works. So you could do it that way as well. But the way I like to do it is I like to do it this way. It's the derivative of the speed. And because if you think of it, this tangential component of acceleration, that's what is changing your speed. How much is your speed changing? If your speed is not changing at all, then there is no tangential component of acceleration. If you're going a constant speed, it's only when you mash the accelerator or the brake, that's when this changes. That's when you get a tangential component. So I find that to be the easiest way to do it, but after I do it that way, you might say, ooh, no, I don't want to do it that way. Okay, so let's do it that way. We'll come back to the normal component in just a minute. So where am I? Where is my, okay, we're back to the front. We're back to the front. So I'm going to do the derivative of the speed. And so now you see maybe why I wrote my speed this way. So the derivative of that is going to be 1/2 times 1 plus 4t squared plus 9t to the 4th to the negative 1/2 power times, chain rule, 8t plus 36t cubed. Okay, double check my work here. And notice what I've done is I've rewritten that as a square root, as a exponent of 1/2. And then I did the multiply by 1/2, reduce that 1/2 by 1, becomes negative 1/2. And then the chain rule says take everything under the radical there and multiply by its derivative. So there you go. Okay, so that's the derivative of the speed. And then we're going to just do the derivative to get the tangential component at 1. There, I'll just put a 1 there to make it look good. So here, tangential component at t equals 1 is going to be 1/2 times 1 plus 4 plus 9 to the negative 1/2 times 8 plus 36. I'm just plugging 1 in for everything. 8 plus 36 is 44. Is that right? Yeah, why am I having trouble here? So 44 divided by 2 is 22. So 22 over the square root of 14. There, good enough. So that's tangential component of acceleration. That, and the units, by the way, the units, meters per second squared. It's an acceleration. So how fast are we going? How fast are we changing our velocity? Okay, let's do the normal component. Or any questions about tangential component? Kind of makes sense. You could do the dot product, the whole vector projection. You'll get the same answer, by the way. In fact, dot product of, okay, so here's how that would work. Dot product, you would do the dot product of, let's see, this dotted with this over the magnitude of that. That actually feels simpler, doesn't it? Conceptually, I don't like it. But it's, you get the same answer. It's 22 over radical 14. So yeah, you want to do that way, you go right ahead. Yeah, that's by the way, that's the vector component. This one, the scalar projection. Okay, let's get back to our picture. So I don't know if you noticed this, but there is a right triangle. Whenever there's a right triangle in a problem, you should at least think that there might be a Pythagorean theorem. And in fact, in this case, there is a Pythagorean theorem involved in this. What I'm going to do is I'm going to take this a of t and turn it into a scalar. That's the length of this. And now you can see, hopefully, that the Pythagorean theorem we're going to apply is this, that the magnitude of a of t squared plus the, is equal to the magnitude of a sub t squared. I guess a sub t is already a positive number, so we don't need, keep erasing things. So a sub t squared plus a sub n squared. I can rearrange this if I want to. In fact, I will, but it's really not necessary. Square root of the magnitude of a of t squared minus a sub t squared. So all I did there is I solved for a sub n. This I find to be the easiest way to do this. You can also do the orthogonal projection. It gets painful though to do this in any other way. You could do it this way. This happens to be the acceleration times what is called the unit normal vector. And we never went over the unit normal vector, but unit normal vector, it's a pain. It's basically you do the derivative of the unit tangent vector, and you get the unit normal vector. And the unit tangent vector is ugly enough. To do the derivative is just intolerable. So I would suggest using the Pythagorean theorem. So here I don't know of any other good way of doing this. So let's go ahead and we will do this up here. So we have a sub t is equal to 22 over radical 14. We have the magnitude of a of 1. Okay, these are all at 1. So where was a? A, come on, there it is, 0, 2, 6. So what's the magnitude? That's going to be 16 plus 4, 20? No, 36 plus 4, 16. 36 plus 4 is 40, square root of 40. Okay, so that's going to be 2 radical 10. And so now we just use the Pythagorean theorem. A sub n, this normal component, will be a sub 1 squared, or the magnitude of a of 1, which is 40. Take this, square it. So I guess it was kind of dumb of me to simplify that. Minus 22 over radical 14 squared. So you square the a of 1, square the tangential component, put it all together, and you get this nice, tasty answer. Let's see is it really that tasty? 22 squared, what is that, 484? I'm pretending. 4, 8, 4, yeah. I can't do that in my head. Oh, 560. 560 minus 480. Ooh, I can do it in my head. Impressive. Hold on. 560 minus 480 is 80, so 76. Oh no, it erased. 76. You'll have to let me know if I got this right. So 76 divided by 2, 35, 38. I hope that's right. It is? Woo! I impressed myself. That's the only person I can seem to impress, that. And God, I know God is impressed with all of us and takes joy in what we do. I have learned that sometimes you just have to try to not impress others. Just try to be happy with what you do for your own joy. Amuse yourself. Sounds selfish, but it really helps at times because it's impossible to make everyone happy. Okay, but anyway, that's, yeah, I don't know where that came from. So I have joy, though, at 38 sevenths. So there it is, normal component of acceleration. So that has units as well. It's a little bit harder to nail them down. I guess it would be meters per second squared, although what does that really mean in terms of these vectors? It's how much you have an acceleration towards the center. Yeah, it would be meters per second squared. Very nice. Beautiful, isn't it? Look at that. Everyone got 100% on this. So you did great. Any other questions about this, a sub n, a sub t? All right, let's see. We have 10 minutes left. So let us take a look at what we're doing today. I know you're thinking, how could we do anything today? Well, we got something we can do. So give me a sec. I'm going to pull this over. Give me a minute so we can see this. Yeah, look at that. I'm going to be adjusting some dates. So let me explain. Pull this over. So you'll notice here that once I get this on both screens, there I can see it. Okay, so let's just make the adjustment now. So you'll notice that this thing, functions of more than one variable. Oh, that is supposed to be due Friday. No, it isn't. It's going to be due Monday. So let's just do this really quick. And then I'll deal with the fallout. This has there's a domino effect. You know, like once I change one, it's going to change. I have to change a bunch of them. But I'll just deal with this one. Oh, 1 minute after Monday's class. Well, that's nice. Okay. Oh, ends. Interesting. So you've got a little extra time there. Okay, let me go back to this week. So I've just fixed the one thing. I'll deal with the rest. I'll deal with next week later. But for Friday, so here's what we're doing. We have classwork. What? Classwork? Yeah, this is what I was hoping to do this in class today. But it's okay because it's not that hard. So let's just talk about these. You're going to do it for Friday or whatever we don't do today. So what we're doing is we're trying to introduce the idea of functions of more than one variable. And this probably will come as no surprise to you or shock. It is not that complicated. But I want to make sure we're on the same page. So a function of two variables is something like this, where you have two variables, two independent variables, and you can plug in different numbers for those two independent variables, just like you did with a function of one variable. So it's really not that complicated. Like I said, I'm pretty sure you can handle this. We probably don't even need to talk about it, but let's do it anyway. So I'm going to evaluate this. That's really not that hard. It's going to be the cosine. Oh, do I do this as a decimal? I guess I do it as a decimal, don't I? I'm going to do the cosine. So let me find my cosine button of 3 for x. So it's going to be 3. Oh, minus 3. So I guess I didn't need my calculator. Cosine of 3 minus 3 is cosine of 0, which is 1. Okay, that wasn't hard. Now it's asking, what is the domain? Domain means the same thing as it did back in the pre-calculus, and that is what numbers are you allowed to put into this function and what numbers are forbidden. So if you look at this function, is there any number you can think of to put in for either x or y that would cause a problem? And the answer is no. There are no numbers that would be problematic. Here's what might cause a problem is if you had something like this for your function. Give me a sec to switch over to the iPad. So if I had a function like this, now you can imagine problems happening if both x and y were negative. That would be bad. So, you would want x and y. Well, actually, you would want x plus y to be greater than or equal to 0. So that means that x has to be bigger than negative y. Is that the way? Wait, x plus y greater or equal to 0. Yeah, x has to be bigger than negative y. Yeah, so you could have negative numbers. X could be negative 1 as long as y is positive 2. X could be positive 7 and y could be negative 4. So it's okay to have negative numbers just as long as the sum isn't negative. But getting back to this, there are no problems with this function. And so the way I'm going to express this is I will say that anything goes. And that funny looking r squared, all that means is that you're allowing any real number for x and any real number for y. So r squared is actually the real plane, but just think of that as you got two real numbers, and you can have any number you want for either of them. So anyway, there's that one. So I guess we're almost done with this problem 1. The range. So now the range, that's a little bit different, but it's actually not that different. we're dealing with the cosine. And the cosine cannot be any bigger than 1, and it can't be any less than -1. And so the range here is going to be the interval from -1 to 1, including the 1 and -1. It doesn't matter that we have an x and a y in there. The range is still what it is. It's still, you're never going to get a cosine to be bigger than 1. You'll never get a cosine less than -1. So anyway, that's what you're going to do. Let me just double check that that's the way that they want you to write your range. So let's submit that for testing. Wow, I just scrolled through and I got scared. Okay, this domain we can deal with. Okay. Let's talk about this. X minus y over x plus y. I would pick someone randomly, but I haven't been picking anyone. So let's just do a regular normal volunteer with these last couple minutes. Oh yeah, that's right. I wanted to see. Yeah, it liked my thing there. So domain. What could go wrong with G, with this G? Yeah, what do you think, Evan? Yeah, we don't want 0 to be in the denominator. So what could go wrong is if x plus y equals 0. So let's think about that. If x plus y equals 0, it means that y is equal to -x. Y equals -x is forbidden. It's bad. Otherwise, we're okay. So the way we're going to represent that is like an inequality that you did back in algebra class. I know you did inequalities like y is less than 7 plus x. Anyway, you put a dotted line for the place that you can't have, and then everything else is shaded. So this is actually, wait, yeah, y equals -x is the bad stuff. Yeah, the rest of these, what are the rest? Oh yeah, they've just thrown in some distractors to try to make it, yeah, there it is. Well, that was easy. Okay, well, look at that, huh? Okay, so for the rest of these, I think that we're going to have to do these in class. You can take a look at them. It's not that hard. You can also use CalcPlot 3D to see what these look like. But I want to go through some strategies for figuring out what functions look like. And we need to look at more functions of 2 variables. That z is equal to x minus y is one of these. And honestly, I think it's this one here. I think this is the one. So it's letter F. And you don't even know what this is. Well, you might, but it's letter F. And it's Roman numeral 1. So anyway, this is, so yeah, and then it's got a bunch of junk down here that you're gonna have to answer. So we'll do this during class. That's what we'll do. We'll do this during class. It'll be part of our exercise on Friday. So I'm gonna push that back as well. Otherwise, I guess there's nothing due on Friday because I don't want you to get frustrated. So yeah, I think I mentioned that I would print anything you want from CalcPlot 3D. At least one of thing for each of you. So you could start playing around with that and seeing if you can find some cool functions. And then on Friday, I'll tell you how to transmit that information to me so that I can print it. For now, I'm going to fix my my date.